Okay, let A be an n by n matrix, and we've seen that if the determinant of A is non-zero, then A has an inverse, denoted A to the -1. And using row operations on the augmented matrix A augmented with the n by n identity matrix, we can find A inverse. We saw that in chapter 1. Next, in this section, we give a way to find A inverse without using row operations, and instead using determinants and the cofactor matrix. So recall that, well, let C be the cofactor matrix of our square matrix A. And what does that mean? Well, that means that the ij entry of C is this cofactor, Cij, given by -1 raised to the I plus j power times the determinant of the matrix you have by removing row I and column j. Next, we take the transpose, or basically flip this cofactor matrix along the main diagonal, and that gives what's called the adjoint matrix. In Sage Math, the command for finding the adjoint is a.adjugate. And again, the ijth entry of this adjoint matrix of A is the ijth entry of the transpose of C. And what that means, what the transpose means, is it's the ijth entry of the transpose is the j comma I entry of the matrix you're taking the transpose of. And then finally, here's the formula for A inverse. It's you take your adjoint matrix A that we just found and divide every entry by the determinant. Or another way of saying it, take this scalar 1 over the determinant and do scalar multiplication of a scalar times a matrix. This is all very abstract, and let's do on the next page an example. Okay, so suppose we have this 3 by 3 matrix, and the question is find the inverse using this formula that we just introduced. Okay, and the solution is, well, we basically need to find the adjoint matrix. And the adjoint matrix is the transpose of the cofactor matrix. So we need to find the cofactor matrix. And since A is a 3 by 3 matrix, the cofactor matrix will also be 3 by 3. And the entries are, well, let's find the 1, 1 entry of the cofactor matrix. It's -1 to the 2. 2 by 2, because 2 is 1 plus 1, times the determinant of the 1 minor. So that's where we remove row 1 and column 1, and we get this matrix remaining, 6, 3, -4, 0. And then the vertical lines mean take the determinant. So the product of the diagonal subtracted off, and then subtract the product of the off diagonals. And so we get 12. -1 squared times 12, that's just a 12. So that's the number that goes in the 1, 1 position of the cofactor matrix. Next, let's try C2, 1. That means row 2, column 1. In other words, the number that should go here. And I've computed it, it should be a 4, but let's see, how did I find this 4? Well, you take -1 and raise it to, you add these two numbers, so that's a 3. And then you multiply by the determinant of the matrix that remains when you start from the original matrix and remove or delete row 2, column 1. So when you delete row 2, column 1, what you're left with is 2, -1, -4, 0. That's what I copied down over here, and I've taken its determinant. 2 times 0 is 0, -1 times -4 is +4, subtract that +4, and you get 4. And so on. And I'll leave the other calculations up here. Won't go through them in detail, but hopefully you can get the idea. It's very tedious to find this cofactor matrix. Okay, so once we have the cofactor matrix, which I've copied out over here, then we simply take its transpose. That means the ijth term is the ji term of the original matrix. So basically you just flip everything across the main diagonal. The things on the diagonal, 12, 2, and 16, stay the same. The 6 flips over to this position, the 4 flips over to that position, and so on. Just another way of saying this is this 12 here, that's in the row 1, column 3, so in the 1, 3 position. To find out the entry that goes here, how did I get this 12 here? What I do is I look at the flip the 1, 3, which is 3, 1, and that's this. This is row 3, column 1. And that entry is 12, and so that's what goes there. Okay, and so then to find the inverse, all I have to do, now that I have the adjoint matrix, then I have to find the determinant of the original matrix. So the original matrix was this thing here, and I've just decided for no particular reason to do expansion by minors along the last row. I could again choose any row, any column. Just for a change, I chose the last row. Maybe because it has a 0, that will make things simpler. I could have also chose the last column. That would also have this 0. That would help things out. Okay, so 2 times -1 to the 4, because this 2 is in the row 3, column 1 position. So 3 plus 1 is a 4. That's how I got that 4 there. Or you could just remember it goes from plus, minus, plus is how the signs go. Anyway, so then I delete row 3, column 1, and what I'm left with is this 2 by 2 matrix, and I take its determinant, and then I subtract, I add -4 times -1 to the 5th power, because this -4 is in the 2, 3 position, and I wish I had written it plus -4 times this, but anyway, okay, so then you take the determinant of what remains when you delete this row and that column, and that matrix is 3, 3, 3, -1, 1, 3. So to get this, take its determinant, that's 9, minus a -1, which becomes 10, and so on. So we get 64, and so the determinant is 64, and so to find the A inverse, we do 1 over 64. And again, this means you multiply every single entry of the matrix by 1 over 64, and so then I get this. Okay, so a little bit messy and tedious, but it is what it is. Let's apply this to a simpler case of a 2 by 2 matrix. All right, well, the cofactor matrix is, well, the 1, 1 position is you take -1, raise it to the 1 plus 1, which is 2, and then take the determinant of what's left when you delete row 1, column 1. That's just a 1 by 1 matrix, and the determinant of a 1 by 1 matrix is that single entry, and so that's why we have D there. Similarly, I'll leave it to you to find these other cofactor entries. And so here's a cofactor matrix. Then to find the adjoint, we flip it. So the D's and A's along the main diagonal stay the same, but -B and -C are flipped. So we get this. And then the determinant, well, we know the determinant is AD minus BC, and so we get this. And we've seen this formula before for the inverse of a 2 by 2 matrix.